I have a question to Dan and then Bob about their talks. And to be honest, we resolved what I personally feel is the answer of this in a private discussion. But I thought that discussion was interesting enough that I'd like to ask the questions in public so that we can all hear it and see if there's other comments. And so for Dan, I think in his talk he snuck in the answer at a crucial point when he relativized the Coulomb potential and momentum space, P minus P prime. He put in minus I epsilon in using the Feynman prescription. And we know that that's the right answer because because it's unitary and causal and all these things. But if you're trying to treat it classically, you might not do that because, in fact, that tells you automatically there's a pole in the propagator. It has all the usual behaviors of a particle. So you could have put the I epsilons in like you do for retarded Green's functions in classical E&M. And so I'd like him to address that question.
It's on? Yeah, okay. Yeah, thanks, John. Because it's true, I snuck it in the talk. It's not snuck in, it's discussed extensively in the paper because it is the crucial thing. So, yeah, the statement is you have to put some kind of prescription for what happens at the pole because you need to be able to integrate over wave packets. So then you can ask, what are the possible ways I can put an I epsilon prescription in the amplitude? There are 4. There's advanced, retarded, the Feynman one, which is what I put in, and then there's the time reverse version of the Feynman one where positive and negative energies switch. So you can then just check by hand each 4 of those 4 cases and check which of them would allow you to satisfy the optical theorem, and the statement is only the Feynman prescription or the time reversed version of the Feynman prescription is consistent with unitarity. So it's actually a proof that you can't use the advanced and retarded propagators.
So do you have a direct comment, Philip? Okay.
Sorry, I have what I would think is probably regarded by the people I'm asking this question as a stupid question, but I'm going to ask it anyway. What I didn't understand about your talk, Dan, was it seemed to me that you were essentially taking a conventional theory, quantum gravity, and you were saying, well, if I make it unitary, then I find that gravity is quantized, in which case the conclusion seems to be tautological. I don't understand what is the point of that argument. Whereas if I contrast it with what Bob was doing, well, actually, I find that the issues raised by Bob's talk are so complex that I'm not sure whether a discussion of this kind would actually get to the bottom of them. But in any case, that's my simple question.
Yeah. So actually, can I ask now Bob the question that I'd like to ask him, because it's actually related to Philip's point. So when we do non-relativistic quantum mechanics, we often just say, choose a potential, let's say 1 over r to the 6th. And we say, choose a 2-level system. And I interpret your talk as saying that choice would be inconsistent because there's no dynamics associated with those choices, and so the radiation that you require wouldn't be produced. But then it seems like what you're saying is that the only, which is actually, I think, a lesson of relativistic quantum field theory, the only way to do interactions in relativistic quantum field theory, consistent with relativity, is to do it with particle exchange, because you need the radiation, so you need the dynamical degrees of freedom, so you need the particles. And so basically you get forced into the situation that Daniel was doing by saying that you need, basically when you get done with it, you need to have the radiation, the I epsilon, the dynamical degrees of freedom. So that the question is, if we chose random potentials that didn't have radiative degrees of freedom associated, would the the thought experiment that you proposed be inconsistent? And does this imply that all interactions have to, relativistically consistent interactions have to have dynamical degrees of freedom?
Yeah, so, I mean, the very short, but not necessarily complete and correct answer to your question is yes, I would agree with what you said. I mean, to be a little more clear, I mean, you know, what we did is analyze, you know, two consistent interactions, I mean, electromagnetism and at least linearized gravity. And we were really noting that you really needed several features in combination. So if you change one of them, like you change the Newtonian potential to 1 over r to the 6th or something like that, you're looking for a lot of trouble. And I'm not claiming a theorem that you couldn't fix that in some other way, but I am saying that you'd really have your work cut out for you, and I doubt if you could fix it unless you had some other relativistic field theory that gave you the 1 over r to the 6th potential, but gave you corresponding radiation, and so on. So yeah, again, the short answer was yes, I agree with what you're saying.
Thank you. Dan, do you want to answer to Philip?
Yeah, it's an interesting nonlinear discussion. So, if I can paraphrase Philip's question, it was like,
Can you rephrase? Can you repeat the question?
yeah. So my interpretation, it's a perfectly reasonable question, which was, you know, you make this the assumptions I put in the argument are very strong, unitarity in particular. And the conclusion is, well, if you put in unitarity, Lorentz invariance, and an interaction potential, you just find field theory, basically. And that's no surprise. I mean, that it just tells you field theory is a tight structure that arises for good reasons. So I think the value is partially just to make that clear, but also I wanted to emphasize a little bit that it is testable. So you can start thinking, could I test whether the interaction is unitary, right? So that's actually supposed to be the unitarity assumption and Lorentz invariance are, you know, operationally definable statements. So I think it's an interesting question of to what extent can you quantify and test unitarity in the interaction and then justify that assumption.
Okay. There was a question by Cliff.
Yeah, I had a question actually for Janve. So it's really just a novice question about this Schroeder-Newton type story, which I had just learned about. So like there was this, I think this is more of a follow-up on a previous question, but it seems like intrinsically non-relativistic since it uses a Newtonian potential. So my question was, given that we know the full relativistic potential can be computed, has anyone tried adding the nonlinear correction, but with relativity built into it, because we know how to compute it? So in other words, this nonlinear term, but not using a 1 on r static potential, but like the full series. Has that been done?
I think there's some recent work. I don't remember the authors of of the paper. They try to write down a field theory where they have some expectation values built in.
Right. I wasn't even imagining a field theory.
Right.
I was imagining instead of having 1 on r, just adding the tower of higher velocity corrections that complete special relativity. So I don't want to include fields. I don't want to include anything except your ingredients. I just want to correct the Newtonian potential with its known relativistic counterpart. In which case, I think relativity would be built into it. It would be like the first G Newton correction, but all orders in velocity, which should, I think, encode relativity. So I wonder whether that would still be relativistic. Maybe it's a naive question, but
Yeah, I think that would be interesting, but I don't know whether there's work.
Because it's like literally a function, you could just try it. Maybe then my second question was, again, with modifying nonlinear quantum mechanics. So everyone seems to modify the Schrodinger equation. Is there a reason once you've done that you shouldn't modify the Born rule? Like why should I? Yeah, you know, we threw everything out the window, so why don't we just keep going? The whole house out the window. Yeah. Because you would naively think that if you have nonlinearity is proportional to G, then I would change the Born rule by some amount which is proportional to G, and maybe that has a consistent theory, or has that been studied? It seems like a very natural thing to do, especially since they're correlated. right?
Right. Basically, what you use for probability as a function of the wave function, and then what you use for evolution. It seems to be that's two parts of the same problem.
Exactly, right? Because
Yeah.
Gleason's theorem would tell us, like, just generically, if we wanted like a consistent probability, then we would want a Born rule that's an inner product squared. But we're breaking all those rules because it's not unitary. So what if we just go nuts and parameterize it with an EFT? Is it known that there isn't a consistent theory that's relativistic and would look, quasi-unitary sensible with those corrections?
Yeah, I think that's very reasonable, but I don't know the answer.
Okay, cool. Thank you.
Yeah.
Can I ask some more general question about this series, okay? Take gravity, put heads everywhere, quantized in canonical formalism. Of course, there will be some troubles which are solvable. When you are suggesting this kind of theory, when you are considering in-out matrix element, etc., how does it simplify life compared to the canonical quantization of gravity?
I don't think it simplifies anything.
It makes it even more
I agree.
it makes it even more complicated, I thought.
Yeah.
Also, when you are calculating all these kind of things, because there is also prescription. If you calculated in and out matrix elements, then okay, Green's functions which are there are Feynman Green's functions. Then there was a statement by Barvinsky-Vilkovsky, I don't know up to what extent it's proved, just you take Feynman Green's function, replace it by retarded Green's function, and then you are getting in expectation value. You see, anyway, actually, the expressions there are horrible, as we know, because the simplest one is logarithm box. You see, if you go further, for instance, in the third order in Curvature's only action, to write action, non-local action, takes perhaps 100 pages. You know this thing, yeah? There is this kind of calculation by Barvinsky, Gusev, Vilkovsky, etc., etc., etc. Calculation of the things, I mean, one loop, it's only one loop up to third order in curvature. What I want to do with the whole thing, because actually I know what was the original purpose of Vilkovsky. He wanted to get Hawking radiation directly from effective action. But it was not so easy, or better to say it was impossible, because it's horrible expression.
Yeah, I think in this case, can I say? I think.
I have something to say about that. Please go ahead.
Yeah, I wanted to say that the reason is not like this will be the more correct theory, but this is really thinking if there are experiments that would claim to test the quantum nature, we want to see how far the classical way could go, where we hit the barriers that are absolutely not possible. It's just an intellectual exercise, I think. And also, when you think about this, you will find the scale, like Jordan has done, you find the scales where possible deviations could come. Because when you do these formulas, there are these frequency scales and mass scales where it may direct the experiments to look in these regimes. I think finally, the other thing I feel interesting is that when we were talking about this theory, including Schrödinger-Newton and the CWL, the question arises, do we need to have a wave function, or do we need to have operators in order to describe the quantum phenomenology? I think for a long time, Philip says, we don't want the quantum states, we don't want the operators. And then when we do the calculations, we try to describe the quantum measurement process by saying, oh, let's not put quantum states, but let's think about our measurement results. We try to compute only the correlations of our measurement results instead of having to refer to the quantum states of our system. So I think when we're going through this process, it's just a way to try to get a better understanding of what are necessary for describing this physics. I don't think the Schrödinger-Newton itself is a particularly good good theory. You have to go to the measurement, and then you circle back to define gravity. That sounds very absurd, I think. But it does show that in quantum mechanics, we have really two parts of our physics, the unitary evolution part and the quantum measurement part. And sometimes the division is very arbitrary. Do we say that the measurement happens, when I first entered the gravitational wave area, I think there are some old papers where they say that we project the test mass quantum state. We apply a POVM on the test mass. And then later on, we say, oh, we measure the light optical field. So I think you have different places where you cut the unitary evolution and the non-unitary, but you always have this very artificial cut. I feel like when we think about the Schrödinger-Newton or the CWL, we seem to have to face this cut. I think in the more official way, you can say, oh no, there's the cut. Your physics shouldn't depend on the cut, because how can you get a consistent result? On the other hand, if your description of physics depend on these things that are not previously important, maybe we can get inspired in somehow to see maybe there's a more natural way, or there are other ways to treat it. This is just some comments. Yeah.
So I'd like to first rather briefly reply to what Slava was saying, because this is something that Andrei Barvinsky and I discussed a lot quite a while ago, and then to what Yanbei was saying. So Slava's referring to a well-known expansion in curvature by Barvinsky and Vilkovitsky done back in the 90s, actually 80s as well as the 90s. There's 3 famous papers that they wrote on this.
Third one was 93.
That's the last one, but actually if you look at, there's a very long series of papers by them, which I understand that cosmologists call Barvinsky, Vilkovitsky 1, 2, and 3. Okay, and they're very long. But the point is, and this is essentially what we discussed, is that you don't expect corrections to the BV equations at all in the characteristic densities of the universe as it is now, okay? On the other hand, if you go to the situation of extreme high density, both, just ordinary density and also density for T mu nu, then in the very early universe, and we're talking really early, the time that you're interested in, then you don't expect that kind of analysis to be meaningful in CWL theory, because it's become completely non-perturbative. But it certainly doesn't give ordinary quantum mechanics or ordinary quantum field theory. So in other words, in the density regimes that exist now in the universe, the corrections from CWL are utterly negligible, but in the early universe, you wouldn't expect the BV equations to even apply. So then, if I talk about what Yanbei was saying, I mean, essentially, I think what he was saying is that we expect CWL theory, I mean, that's how it's formulated, to remove entirely the need for this cut between measurements, the classical world on the one hand, this arbitrary, von Neumann-style collapse of the wave function, and the microscopic realm. So in conventional quantum mechanics, we have the microscopic realm on one side, we've got classical physics on the other, and we've just got this completely arbitrary cut that occurs when we have a so-called measurement. And a great deal has been said on how arbitrary that is. In CWL theory, you expect that for a massive object, you will see what I was referring to the other day as path bunching. And so what one would like to do is analyze a real measurement and show that happening. But as I also mentioned the other day, to do those calculations turns out to be rather difficult. The dynamics of path bunching is not simple. So in order to address these experiments, this is what both Yanbei and Jordan were referring to, we've actually had to do what I certainly don't like to do, which is, because of course the real experiments are very complicated, we've had to resort to the procedure of calculating the CW dynamics up to a certain point, the point that we believe is important for discussing the difference between what would be predicted by ordinary quantum mechanics and CWL theory, and then imposing the cut. That's clearly not what one should do in the final analysis. That's how I would look at it.
Let's just leave it. Okay. Thank you. Abi?
So just keep the mic because it's a question for you. Just again, reconciling in my head about what Jordan said and you have said before. So, I mean, you just, as I understood it, you said that, well, if I were to apply it for this today's matter density and so on, then the effects are negligible. If I were to apply it to very early universe or near black holes, then since I'm talking about effective field theory anyway, the equation is not applicable. Is that, first of all, is my understanding correct? If so, I'll ask the next question.
Sorry, I didn't quite.
Okay.
I didn't quite hear everything you said.
I'm sorry. Okay. So, but in today's matter densities and so on, the effects, the effects of the type that Slava was talking about, or some other effects, are negligible, and we would be able to get to ordinary. I mean, we just get ordinary quantum mechanics. There's no deviation, or there's no. Yeah.
Well, sorry, no. For the current densities, if we apply CWL theory to cosmological questions, we just have ordinary GR.
Right.
Yeah.
So, but then, but I could not really apply it to the very early universe because it's supposed to be, it's based, as was just explained, on effective theory, and therefore I could not apply it there because it's in the Planck regime, and what are the modifications of dynamics there? I cannot answer this using CWL.
So my point is that the BV equations would also be inapplicable to the very early universe because it's a curvature expansion, and the curvature is fantastically
I'm not
high.
comparing with anything else. I'm
just
trying to understand. Yeah, I'm not saying that something else is not, but so is that correct? First of all, that these, for the obvious reason that seems to be obvious to me, that it's an effective field theory as far as gravity is concerned.
Oh, sorry, yes. Sorry, I now understand your question. Sorry, I'm rather tired, so I find it hard to concentrate. But yeah, you're absolutely right. The CWL theory is not a theory which you should extrapolate to the Planck energy.
Right.
That's correct.
So these, some of the deeper questions that people are asking about, what happens at the Big Bang, or what happens, in the Planck regime around Big Bang or black holes, that's outside the scope of this theory.
That's right.
Okay, thank you.
So, I would have had a question for Dan, but he's gone, so. Yeah, exactly.
He knew you were going to
Yeah, he knew, exactly. Okay, I grab him. So, excellent. We are close to lunch. I think lunch will be finished, will be done in 5 or 10 minutes. If there are no more questions, and if Dan will not appear within the next 5 seconds,
Sorry, I just need to make an announcement.
well, then I close the discussion session and hand the mic over to Philip for an announcement. Thank you very much to all the speakers and, of course, all the discussants.
Can people hear me? Yes. Yeah, so I just want to, first of all, reiterate that if anyone wants to sign the statement that that information is lost down a black hole, then the paper will be out on the desk where Swan usually sits. Okay, so the real announcement here. If people want to visit D-Wave on Friday, I gather there are 1 or 2 people who do, the thing to do is give your name to Swan, so that she can then give the list of people who want to go to D-Wave so that they can organize the transport there and back. I actually don't know. I don't know. Yeah. Today, 2 o'clock. So we reconvene here at 2 p.m. I don't know. Oh, so Birgitta says yes. Okay, this has got nothing to do with me, so I don't know, right? So she says 10 years ago they did. Yeah, okay, Bill, never mind, okay? I don't know the answer, so ask Swan or whatever. Okay, right. Sorry, you want to ask me a question? Okay, I'll give you I'll give you the mic, Slava.
So, okay, signing collective letters, I don't think that it's a good thing in science. You understand? And, okay, because I come from Soviet Union, I know that all collective letters is P.
I think I'll make one remark, and then Renata wants to make a remark. My remark is that we're not in the Soviet Union. And also, I would like to remark that, as I know very well, you once had a vote in a meeting on whether or not people believed in the many worlds theory. So, so you know, either you're in the West or you're not.
Yeah, well, I support on different grounds what Slava said. So, you know, I think, of course, the question is somewhat context dependent, and there are, of course, quite a few people in this audience who would believe that the ultimate answer requires quantum gravity. So it could backfire if people say, oh, yeah, look, whatever, you know, maybe you like 90% of people are of one opinion, and then, well, what's the need? So, you know, everyone's of one opinion. What's the need for your institute?
Actually, I think that's a very good point, because I think that that people, yeah, I mean, I think that Bill, look, I'm not going to speak for these other people that made these statements yesterday. I mean, Kip said basically exactly what you said. We don't know the answer until we have a theory of quantum gravity. And I think that's more or less what Roger said as well. And I don't know, so should we modify the statement to this question cannot be answered until we have a theory of quantum gravity? Sorry, can you take the mic?
Andy Ströminger, who was speaking so much about information paradox, etc., etc. Now, last time when I have seen him 3 months ago, he's not sure anymore. Is this paradox or there is no this paradox, etc. And then, okay, you go to Advanced Study Institute, of course, they will tell you that there is, and we swore with all our authorities that there is this paradox. But I think most of these people just do not understand what is the structure of the black hole. This is the only trouble with them.
Philip, I believe you yourself were a little bit critical of Maldaceno's usage of the word dogma in their central dogma, and I would hate to be dogmatic in the opposite direction.
Yeah, I'm not sure that it's dogmatic to say that we believe a problem has not yet been solved. Oh, sorry.
Just one quick comment. If you had the theory of gravity, which would explain gravity, would it not also explain quantum gravity? It should explain any facet of gravity that we see as unique if you have an overall theory of gravity. For instance, if you have an overall theory of a human being, you would explain all 3 states, subnormal, normal, and advanced.
Peter.
I think one of the exciting features of the quantum gravity effort here is to bring together different communities that have different backgrounds, different starting assumptions, and to put them into dialogue. So it seems to me to work slightly against our aim of being polyvocal, to already start with a statement that we have the view and we know what it is, and here's the result.
I second that.
Yeah, Cliff.
I feel any statement of certainty would put me on the opposite side of that claim. So I would then have to disassociate myself from any statement that we know anything. Yes.